Before your eyes is the construction site of Rogun Dam in Tajikistan, where thousands of workers and machines are racing to complete a project expected to become the tallest dam in the world. This structure will stand about 335 meters tall, located on the Vakhsh River, and is expected to become Tajikistan's new energy center. But to complete it, engineers must overcome extremely dangerous risks, strong earthquakes, a foundation sitting on a salt layer that can be dissolved by water, flood flows with enormous destructive energy, and tens of millions of cubic meters of earth and rock. So how did they build the world's tallest dam on such a complex geological foundation? Let's find out in today's video. Before we begin, please hit like and share this video to give us more motivation to continue making higher quality content. And now, let's get started. To understand why Tajikistan dares to pursue a project as difficult as Rogun Dam, we first have to look at the country's terrain. Tajikistan is a mountainous country in Central Asia. Most of its territory is covered by high mountains, making transportation, agriculture, and large-scale industrial development all highly limited. But that same terrain also creates a major advantage: hydropower. Water from snow and glaciers in the mountains flows down into deep valleys, creating rivers with steep gradients and very strong energy. Among them, the Vakhsh River is one of Tajikistan's most important hydropower sources. With Rogun Dam, Tajikistan does not simply want to build another power plant. They want to create a reservoir large enough to regulate the flow, generate electricity more stably, and gradually turn the country into a power exporting hub in Central Asia. That is why they chose the most ambitious option, building a dam about 335 meters tall. But that height also increases every risk: greater water pressure, heavier loads on the foundation, and in an area with a high risk of strong earthquakes, Rogun Dam cannot be built like a conventional concrete dam. To deal with this problem, the solution chosen was an earth rockfill dam with an impervious earth core. In terms of structure, the dam body is divided into several different material zones. At the center is the impervious earth core, whose role is to limit water seepage through the dam body. Surrounding the core are filter layers and transition layers, which help stabilize the fine materials while also preventing internal erosion when seepage occurs. On the outside is the rockfill shell, which creates mass, stabilizes the dam slopes, and distributes loads down to the foundation. The important advantage of this dam type is its ability to perform more flexibly under earthquake loading. When seismic shaking occurs, the dam body can undergo small deformations within allowable limits. Thanks to this, it absorbs part of the seismic energy instead of suddenly cracking like an overly rigid concrete structure. In other words, Rogun Dam does not resist earthquakes through absolute stiffness. It resists earthquakes through its massive weight, zoned material system, and controlled deformation capacity. But solving the dam body is only half of the problem. Because even if Rogun can withstand seismic shaking, engineers still have to face another risk deep beneath the foundation: how to prevent reservoir water from seeping down into the salt layer below. The problem lies in the very nature of this salt layer. Salt can dissolve in water. Therefore, if reservoir water seeps down through cracks in the bedrock, it can come into contact with the ionox salt layer and gradually create voids beneath the structure. For a dam about 335 meters tall, that is extremely dangerous, because once the foundation is weakened, the overall stability of the dam is also threatened. Therefore, the engineer's task is to block the seepage flow before it reaches the salt layer. The solution used is a grout curtain. Engineers drill deep into the bedrock, then inject high-pressure cement grout into fractures and weak seepage zones. When the grout hardens, it creates a deep, underground, watertight zone, helping reduce the risk of water reaching the salt layer. Put simply, if the dam body is the part that holds water above, then the grout curtain is the protective layer for the foundation below. After handling the foundation problem, the next challenge is building the main dam body. With Rogun Dam, this is not about pouring concrete into a single solid wall. The dam body is formed from a massive volume of earth and rock, reaching tens of millions of cubic meters. To obtain enough material, earth and rock must be excavated from quarries near the construction site, then crushed, sorted, and continuously transported to the dam placement area. If only dump trucks were used, the construction site could easily become congested. That is why Rogun uses an industrial conveyor belt system to move material from the quarry to the valley at a more stable rate. When the material reaches the construction location, bulldozers spread it into layers according to the designated zones in the design. Then, the earth and rock layers are compacted to achieve the required stability before the next layer is placed on top. This process repeats continuously: excavation, crushing, transportation, spreading, and compaction. Layer by layer, the dam body gradually rises above the Vakhsh River. The important point is that each type of material cannot be placed randomly. Materials for the impervious core, filter layers, transition layers, and rockfill shell must all be controlled separately. If the gradation or placement is wrong, seepage paths can form inside the dam body, increasing the risk of internal erosion or long-term instability. Therefore, the construction of Rogun Dam is not just about moving as much earth and rock as possible into the valley. It is a layered construction process where every cubic meter of material must be placed in the right location with the right size and the right compaction. Only by doing that can the dam body withstand water pressure, earthquakes, and deformation throughout its operation. But the dam body is only one part of Rogun Dam. To turn the water flow into electricity, the project also needs a massive power generation system. The special point is that this powerhouse is not built exposed on the surface, but is placed deep inside the mountain. Inside the mountainside, engineers excavated an underground space about 220 meters long and 78 meters high, large enough to contain generator units, turbines, and auxiliary equipment systems. This layout helps protect critical equipment from the risk of surface rock slides, while also using the surrounding mountain mass as a natural protective layer. But in return, excavating a huge powerhouse inside the mountain is also a very difficult engineering challenge. When a large volume of rock is removed, the stress state inside the rock mass changes. If it is not properly reinforced, the tunnel roof can crack, the walls can deform, or groundwater can enter the construction area. Therefore, building the underground powerhouse is not just about digging a very large empty space. It includes drilling and blasting, rock removal, tunnel wall reinforcement, groundwater control, and equipment installation in a confined space. When completed, water from the reservoir will be led through pressure tunnels down to the turbines. There, the energy of the water is converted into mechanical energy and then into electrical energy to supply the power grid. In other words, if the dam body is the part that holds the water, then the underground powerhouse is where that mass of water is turned into economic power for Tajikistan. But a large dam does not only need to store water and generate electricity, it must also be able to release floods safely. For Rogun Dam, this is an extremely important challenge because the Vakhsh River can carry flood flows with very large energy. If flood water is released straight down to the dam toe, the high-velocity flow can scour the riverbed, damage the bedrock, cause erosion, and threaten the downstream area. Therefore, the spillway system must be designed to reduce the energy of the water before it returns to the river channel. One of the solutions used is a flip bucket structure. Simply put, this is the concrete bucket section at the end of the spillway, designed to throw the flow into the air instead of allowing it to plunge directly down to the foot of the structure. When the water is projected outward along a calculated trajectory, part of the flow energy is dispersed before the water falls downstream. But this design has to be extremely precise. If the impact point is too close, the water can damage the dam toe. If the impact point is too concentrated, it can create a large scour hole in the riverbed below. Therefore, with Rogun Dam, flood release is not simply about opening gates and letting water flow out. It is the process of controlling a massive body of energy so that the water leaves the structure without coming back to destroy the area beneath it. In other words, if the dam body has the task of holding water and the underground powerhouse has the task of generating electricity, then the flood release system is the final protective layer when the river becomes too powerful. What makes Rogun Dam special is that it is not a new idea. This project was started during the Soviet era, with the first groundbreaking in 1976. At that time, Rogun was envisioned as part of a large-scale hydropower system on the Vakhsh River, continuing the massive projects that the Soviet Union had built in Central Asia. But then, history changed. After the Soviet Union collapsed in 1991, Tajikistan fell into crisis and civil war. The Rogun construction site was abandoned, many structures remained unfinished, and materials and equipment were no longer maintained as before. On top of that, in 1993, a major flood swept through the construction area, washing away the unfinished cofferdams and forcing many parts of the project to begin again. From a project planned to become an engineering symbol, Rogun became a project trapped between lack of funding, instability, and geological challenges. In the years that followed, Tajikistan still did not give up. There were proposals to lower the dam height to reduce costs and generate electricity sooner. But for Tajikistan, Rogun was not just about building another power plant. They wanted to maximize the potential of the Vakhsh River, create a larger reservoir, greater capacity, and a stronger energy position in the region. Therefore, the project continued to be pursued under the ambitious option, a dam about 335 meters tall. This makes Rogun not only an engineering project, it is also a project carrying national ambition, stretching across generations, from the Soviet era to modern Tajikistan. A project lasting nearly half a century requires a massive and continuous flow of money. This is a very difficult problem, since Tajikistan is not a wealthy economy. To keep the construction going, they have been forced to raise capital from the state budget, international bonds, and financial institutions. Recently, the World Bank approved a $350 million support package, providing a crucial resource to keep the project moving forward. However, the costs of the Rogun Dam do not stop at materials or construction techniques. The project also consumes a huge budget for foundation treatment, building the underground power plant, and especially resettlement costs. As the reservoir rises, tens of thousands of people are forced to relocate, trading their homes and familiar lives to make way for the project. Therefore, the Rogun Dam is a massive economic gamble and a huge social trade-off. Tajikistan is betting that future revenue from electricity exports will be large enough to make up for the financial burdens and social losses of today. The Rogun Dam is not just a hydroelectric megaproject. It is the biggest gamble Tajikistan has ever placed on its future. By successfully solving the harsh challenges of geology, engineering, and finance, the project will help this nation break through and elevate its energy position in Central Asia. But if it stumbles, the dam will become a colossal economic burden. If you enjoy the engineering stories behind mega projects like this, please subscribe to the channel to watch our upcoming videos.